Okay, so for part three here, we left off talking about linearly independent vectors at most two vectors in R2 and at most two vectors in R3. Did you think of a way to tell if you have whether your set of vectors is linearly dependent in Rn? Hopefully you came up with the following two rules. Rule one, if you have more than n vectors, it will be linearly dependent. So for example, when we did this guy up above and we had four vectors in three-dimensional space, R3 here, then they were linearly dependent. So if you have more vectors than the size of the space, we'll have a lot more to say about it very soon, then it will be linearly dependent. There's another one that I hope you caught. If your set contains the zero vector, then he is automatically linearly dependent. Okay. All right. So next up, let's talk about other things that are not arrows, but other vector spaces. So for example, P2, polynomials of degree at most 2, is this set of vectors, x plus 1, x squared minus 1, and x squared plus x, linearly independent or not? Well, what we need to do is check it out. So C1 times x plus 1 plus C2 times x squared minus 1 plus C3 times x squared plus x. And is that equal to 0x squared plus 0x plus 0, aka the zero vector in P2 under standard operation? Well, that will set off a system. If we look at this, this is going to be 0x squared plus C2x squared plus C3x squared equals 0. So we've got 0, 1C2, 1C3 equals 0. So the x squared line, if we look at the x coefficients, we've got C1x plus 0C2 plus C3x equals 0x. It's going to give us the row like this. And finally, the constants will give us that. And let's RREF this matrix. When I RREF the matrix, I get this, which tells me that C3 can be any parameter, since I have two non-zero equations in three variables, C1, C2, and C3. C3 can be t, then C2 would be negative t, and C1 would be negative t as well. So if I let t equal 1, that would tell me that 1 times x plus 1, actually I'll make it be negative 1. So 1 times, negative 1 times this guy, well, that makes it a positive 1, plus 1 times x squared minus 1 minus x squared plus x is equal to 0. And you can see if we do x squared minus x squared, we get 0. X minus x is 0, and 1 plus a negative 1 is 0. So we can then say that x plus 1 is negative x squared minus 1 plus x squared plus x, solving that guy, showing that the first vector can be expressed as a linear combination of the second and third. Similarly, we can show that x squared minus 1 is negative of x plus 1 plus x squared plus x. Okay. And finally, that x squared minus x, we can solve for him and find out that he is x plus 1 plus x squared minus 1. Oh, sorry. Did I goof up? Yeah, I made a mistake. It's x squared plus x is equal to x plus 1 plus x squared minus 1. So you can see that any one of these three vectors in our set could be written as a linear combination or scalar multiples of the other guys. So this set is linearly dependent. Okay. Now, can you think of a set of nice vectors in P2 that are linearly independent and span? Pause the video and then come back and see if yours agrees with what I thought of. So how about the vectors x squared, x, and 1? If we think of those guys, we can take and make any polynomial of degree at most 2, ax squared plus bx plus c, by using a of the first one plus b of the second one plus c of the third one. But it shouldn't be too surprising, since we've made our connection between polynomial space and vector spaces, that this guy is in fact like 1, 0, 0. This guy is 0, 1, 0. And this guy is 0, 0, 1. If we look at these as the x squared, x, and constant coefficients. And so these guys behave just like I, j, and k did earlier. So they must be linearly independent. And we've shown that you can hit any vector you want and span all of polynomials of the most 2. Okay. And one aside here, this guy is like the vector 0, 1, 1. This guy is like the vector 1, 0, negative 1. And this guy is like the vector 1, 1, 0. And those three vectors are linearly dependent. Okay. All right. Let's go and try another space here. What about matrices? In 5.1, we showed that matrices under standard operations are also a vector space with real coefficients. Are the matrices 1, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 1, and 0, 1, 0, 1 linearly independent? Show your work and explain your answer. I'll go ahead and pause the video and then we'll get back in just a minute. Okay, we're back. So I put into the definition of linear independence, did a linear combination of our basic, our set of vectors here, and see if they were equal to the zero vector under standard operation. And we find out that we do get some non-zero choices that will work, so these must be linearly dependent. Okay, and in fact, we could write negative 1 times 1, 1, 0, 0 plus 1 times 1, 0, 1, 0 minus 0, 0, 1, 1 plus 0, 1, 0, 1 is equal to 0, 0, 0, 0. And that will allow me to solve for any one of those three matrices in terms of the other. Now, again, this is probably not too surprising, but can you think of a nice set of vectors to be linearly independent and span all of them to 2 matrices that are 2 by 2 with real coefficients or real entries? Go ahead and see if you come up with the same ones I do. Pause the video. All right, so we're back. How about using that? And you can see that because if I wanted to make I can say the first, let's do the second, let's do the third, let's do the last one. And there's no way that I can get any one of these to the multiple other guys. So these guys are linearly independent. But this shouldn't be too surprising, as we saw that matrices are a vector space. And so the matrix 1, 0, 0, 1 corresponds to the vector in R4 if we read left to right, top to bottom, 1, 0, 0, 1. And the matrix 0, 0, 1, 0 would correspond to the 4 vector 0, 0, 1, 0. And under standard operations, we know that R4 will behave like a vector space. So you could then see that these guys, 1, 1, 0, 0, 1, 0, 1, 0, etc., these guys actually would not cover all of 4-dimensional space because they are linearly dependent. And we'll have even more to say about that. Now, we also saw in chapter 5